Hello and welcome to Toddcast number 47. We're going to start into alkyne reactivity with the next three Toddcasts, 47, 48, and 49. And what we'll quickly come to learn is alkyne chemistry is very similar to alkene chemistry because, after all, you're reacting with a pi bond. Alkynes have two pi bonds to react with, so that makes them I don't know, they'll react a little differently than alkenes. But the other thing also, just to emphasize, is the pKa for sp3 versus sp2 versus sp carbons for the hydrogen attached to those gets gradually more acidic, gets a lower pKa. So whereas sp3 and sp2 H's unlikely to be deprotonated, we actually have the means to deprotonate an sp carbon to hydrogen bond. So we can deprotonate alkynes to make them a nucleophile. So in that sense, we actually already have started into alkyne chemistry because alkyne anions, alkynyl anions, have been just involved in our SN2 reactions earlier. So there's basically going to be three podcasts. The first of which is going to cover just some review of reactions you've seen. Second one's going to emphasize how similar they are to the alkene reactions. And the third one's going to involve their use in synthesis, amongst an overview of some of the more complicated reactions. So hopefully this all works well for you, but we'll go ahead and start with the basics of alkynes. We covered them briefly in early podcasts, but I want to just reiterate what we covered. So first and foremost, they contain a C triple bond C. The thing to remember is that would mean a sigma bond, and then also two pi bonds, which cannot be in the same plane. So then they're in perpendicular planes. So we'll look at their structure briefly. So each of them are sp hybridized, which means they have a 180 bond angle, so they're linear. As a consequence of being linear, because of that 180 or linear nature, they're good nucleophiles when deprotonated. So if I get rid of this H, they're phenomenal nucleophiles. They have no lone pairs and two atoms attached. Each carbon, one is attached to the other carbon and an H. In this case, this one's attached to a carbon, another H. So alkynes always have one sigma bond to a carbon and then one sigma bond to one other atom. Again, linear in nature. And this orbital picture for just acetylene, this molecule right here, hopefully seems reasonable. The carbons are darkened in. That is your triple bond, although it's represented by a single line. I'm going to just emphasize that there's a triple bond there. So they're held together by two pi and a sigma bond. It's a very strong bond. Triple bonds are the strongest. And then two CH bonds. Okay. 180 angle, as mentioned before, the bond lengths about 1.1 and about 1.2, give or take. So one to just consider various alkynes. So again, triple bond. So I'm going to emphasize that you can have CH3 groups or any R group for that matter at the end. So this is going to be known as an internal alkyne. Hexyne, 3-hexyne, same thing, internal. So it's between 1, 2, 3, and 4. And so just emphasize that there's a carbon here and a carbon here. They're unwritten in this bond line notation. But they can also have an H on one side and an R group. So this is what's known as a terminal alkyne. So terminal, meaning the triple bond is between carbon 1 and carbon 2. And that makes this proton right there kind of acidic. pKa equals 26, roughly. Okay. So we have our alkyne trivia. Want to look at the structure. So the sigma bond, we'll emphasize that at first, the sigma bond between two carbons is here. The other sp hybrid then can form an sigma bond with an H. And so this is our atomic connectivity as far as sigmas go. So sigma between C, sp, and the H, 1s orbital. Same thing over here, the 1s orbital of H with the sp of carbon. And then these two SPs. And the black circles represent where the carbons are located, where the nucleus is located. Relatively speaking, from a size perspective, it should be a much tinier dot, but this will work. You also have perpendicular pi bonds. So this is one p orbital, another p orbital. When they interact, they should be slightly bent towards one another, but for this picture, it'll be fine. So if this one is in the vertical plane, then the other pi bond must form in the horizontal plane. So we come together, and that's your overall picture of how it works. So you have one pi bond here, and then a second pi bond there. So perpendicular plane pi bonds. So lots of pi density. Can also draw it in this sort of picture. So again, want to emphasize just the pi bonds, vertical and horizontal. And then again, sigma bond between C and H, and then the sigma bond within that structure. So hopefully these seem okay. So these are the bonds I've mentioned on the previous slide. Okay, relative acidity, again, note that SP is more acidic, so the more S character, 50% S, will make it more acidic. So pK again, roughly 26-ish, 40 and around 49. These numbers get to be so drastically large, and keep in mind that means a K of 10 to the minus 26, 10 to the minus 40, and 10 to the minus 49. The precision of those numbers, not that great. So these are in the ballpark. We measure them relative to one another, how they react, but this is the only one we can consistently pull a proton off. These, far more challenging. So again, one reaction you've already seen, the SN2. So the alkyne won't be good at attacking, but if I deprotonate it, I should be able to do this. So very common reaction. Add in a base that's a little bit stronger. So if you had a base whose conjugate acid has a higher pK and therefore a weaker conjugate acid, then LDA will be the stronger base, for instance, and it'll be able to pull that proton off. So you generate a great nucleophile. So once you get rid of that H, you have this, which can come in and attack pretty much anything. So CH3 and whatever leaving group. So I could put iodine, bromine if I want to stick with halogen, could put OTOS if I want to start from an alcohol and convert it into something more reactive. Lots of different options. But basically, this lone pair is going to come in SN2 style and kick those electrons out. So SN2 reaction. Bases such as LDA, lithium nitride, or amide, I should call it, and butyl lithium will all work. And then just to note, there's a T-butyl lithium and an N-butyl lithium, straight chain, and I'm going to use them pretty much interchangeably. But extremely strong bases have a negative on N, negative on an N, and negative on an sp3 carbon. So pK around 37 for the conjugate acid, pK 38-ish for the conjugate acid, and pK, as we already said, up in the 40s, high 40s, butyl lithium. Every one of these pKs is greater than this, so if it's a weaker conjugate acid, then it's going to be a stronger base than this, so the equilibrium will lie in the forward direction. So if, well, actually written here, if I choose butyl lithium with a pK of conjugate acid pK 49, and this one 26, if you remember, it's the K is equal to 10 to the product pK minus the reactant pK. And so if this is 26, and then the product we form is 49, 10 to the 49 minus 26. Maybe make that a little more size relevant. Was 10 to the third, highly favorable reaction. Okay, so we're set. This is definitely a reaction that you will see when you deal with alkynes. So the stronger acid, weaker acid is more stable. Reactions always go to the side that's more stable. So the two stronger reagents react and form two more stable, weaker reagents. So your typical synthesis, just recognize this. You're in a deprotonated terminal alkyne. So let's say we start with the simplest one, where it's just a two-carbon acetylene. We can deprotonate one of the H's, and it could be left or right. They're equally acidic. So you have used, this case, I used N-butyllithium. Then I'm going to add some R group, and I'm going to add it at either primary or secondary carbon because it's going to go by SN2. So in this case, it's primary. So I end up with that on one side. I have one more H to react, so I can deprotonate it, use a second equivalent of this, deprotonate it. And when I do, this becomes a nucleophile once again. And I'm going to attack this time, call it R double prime, so a different R group. So ultimately, we can get an alkyne that has two different R groups on each side. So this one, let's say, is two carbons. This one might be three. This could be seven. This could be 12, whatever we choose to react with. But very common to deprotonate the hydrogen on an alkyne, make it a nucleophile, and attack an alkyl halide, make a longer alkyne. Very typical. How do we get alkyne? So we have one reaction we've seen to spend them, this nucleophilic reaction. Let's also consider how we get them. So we get them actually by double elimination. So a single elimination, if you recall, an E2 or an E1 generated an alkene. So do that same reaction twice, and guess what? You end up getting an alkyne. And so it's kind of convenient in this case. So the first one acts just like an SN2, or E2, my apologies. So notice the heat, just like you have to always add if we're making an unstable pi bond. So it has to be anti. So if I choose this H and this Br as shown, then the Br is going to be down and H is going to be up, which it is. They stay anti to one another. And so I simply do the same reaction again. When it's vinylic, meaning when it's H is on the double bond, the Br also in the double bond makes it more acidic. So trans makes it more acidic. So the Br pulls electron density away by inductive effect, which in turn will pull electron density away from the H. It makes that H more acidic. So if you've learned this in physics, when things are in a straight line, when two forces are in the straight line, they're stronger. So if I have those two forces, they're not in collinear, but they're in the same direction. It's going to be a much stronger force than if they were going here and here, for instance. So when they're anti to one another, when they're trans across the double bond to one another, it makes the H more acidic. So it's going to be more susceptible to being removed. So once again, add a base, add some heat, another E2 elimination, and I end up with this. This one I'm going to put in question marks because although I'm using the same reagents, the mechanism for the second one coming off is similar but not exactly the same as the first one. And it's just has to do with the orbital alignment. So no major concern, but the question mark there, it is E2-like, is what I should say. Okay, so let's consider if the two BRs are on different carbons, so how that'll work. So this one ends up that now we have competition between this H eliminating with this BR or this H eliminating there. Well, it ends up the one that is anti to the BR is going to be more acidic than the one that is not, so that helps. So this H and this H are more acidic than H's on the terminal ends. So you're going to end up getting, once again, the double bond internally. And as long as the H's and BRs are opposite one another, then this H becomes your most acidic hydrogen, the one that is trans and coplanar with the BR. So we end up getting the same thing. So just like above it worked out, so it could be two BRs on the same carbon, or it could be on neighboring carbons. We'll end up getting the same thing. And again, E2-esque. So let me say these two. They're not exactly perfectly what we get with an E2, again, because the orbital alignment is a little different than what we normally look at, but it's close enough to E2 that we're going to say the same conditions and the same end result. Okay, both reactions, the second elimination. So a little bit harder to get the second elimination, but it can be done with good enough, strong enough conditions. So, and luckily, it ends up forming almost exclusively between the same carbons. Okay, so that is a revisit of some of the reactions you already know about alkynes. So the next podcast, we will focus on reactions that you don't know yet, but you've seen them in alkene chemistry and should pick them up fairly quickly. So with that in mind, thank you for joining. I will end this podcast and I will